So is this the first situation in which you can see new life, this new complexity?
So I think, yes, so we won't find life in here per se, but because we're putting in a code, what we're doing in here, we will make complex molecules, more complex than you can find normally, but we will understand how much code, how much we had to cheat. And by them writing down how much we had to cheat, we can then work out randomly how long it would take. But at least by doing this, we will know how by chance it will be. So this gives us the odds. Is it 1 in 20, 1 in 1,000, 1 in 200 million, or 1 in infinity?
Within a few 100 million years, there's evidence in the fossil record that life formed simple cellular life. Those two facts are not, as far as I know, disputed by
those are not contestable. How we got from the point A to point B?
Absolutely, but I did not say we knew.
Right. So we're agreeing. Okay. You and I agree, Lee, that how we got from the simple molecules to life, it happened, but we don't know how.
Exactly.
In this ooze emerged the first life.
I find it problematic in that there's an extrapolation from a very small experiment in a laboratory.
Researchers have now created life from non-living parts.
There were many kinds of molecules in the primordial soup.
I'm boiling up some primordial soup.
Your entire civilization, it all begins right here in this little pond of goo.
You see, when I pushed him and pushed him and pushed him, we don't know how. Absolutely. Shortly after the heavy bombardment, shortly after the cooling of the Earth, boom, there's life. That's all we know.
It's very difficult for me to understand whether he misunderstands the term or whether he's just deliberately trying to mislead because it doesn't generate the correct narrative. And I guess maybe it's a little bit of both. He's suffering from kind of cognitive disconnect because he believes that his view is so correct. But it seems rather contradictory because he uses catalysis in his laboratory to make molecules all the time, to make molecules that you could not make in a billion years without that catalyst. Yet when he adds the catalyst, he gets his molecule and he's able to accept that. So for me, his understanding of catalysis seems to be selective use of science and non-science when he then disses it in the next. So I think there's something rather nefarious in his statements. I don't think it's because he's being stupid. I think it's because he's being selective and he is misquoting information so that people can go into literature and see something and then make a connection without fully understanding it.
Nefarious. I'm rather nefarious in what I'm doing because I'm going against the consensus here. What does nefarious mean? Well, it's typically an action or activity wicked or criminal. Okay, so what I'm doing is either wicked or criminal. Well, it's probably not criminal. I'm not going to go to prison for this, but it's wicked. But I gave the man a chance to explain it, and he couldn't.
So why has no one made real life from scratch? All the people that have made life in the lab have cheated. They have taken existing building blocks, and those building blocks were produced by evolution. And that evolutionary process goes back to one genesis point.
You just said that all the people that have made life in the lab have cheated. Tell me, Lee, give me an example. Show me that reference where someone made life in a lab. Nobody has ever made life in a lab. And you guys keep putting this out there, and that's why the world is so confused. This one's on you, Lee. This one is on you. You start saying people have made life in the lab, and you don't like the way they've done it because they've done it with organic molecules that are already existing. Nobody has ever made life in the lab. Show me that reference. You can come on my channel and show me. Go on Dave's channel and show me. No one has made life. You said all the people that have made life in the lab have cheated. There was a survey taken. Under simulations of early Earth's atmosphere, scientists have mixed molecules together in laboratories to produce complex life forms such as frogs. 2/3 of the population believes that that is false. 1/3 believes it's true. Under simulations of early Earth's atmosphere, scientists have mixed molecules together in laboratories to produce simple, single-celled life forms such as bacteria. 2/3 of the population believes that that is true. 2/3 of the people. Where might they have gotten that? Tell me how those small molecules got to be big molecules that had the right symmetry, the right properties, the right elements to them that then formed, and how did they polymerize, and then how did that form life? Tell me. You don't know. So say it with me. You don't know. You're the one that's confused these people. Who are these people? Well, the average age is 38. Their sex was half male, half female. And how educated were they? Well, 80% of them hold college degrees. 80% of them.
And the idea we've been playing in my lab anyway is to try and make drugs using robots and try and understand the digital information. How big does my program need to be to make the molecule? And that's how we got thinking in this way. Or actually, it's the other way around. I needed money to build robots to search for the origin of life, and no one would give me any money for that. It's like, no, I'm going to make drugs for you instead. Then you can get money.
So what Lee Cronin wants to do, he wants to build robots to explore the origin of life. He can't get money for it, so what he does is he tells the funding agencies, I'll make drugs for you. And then he can get his money. That's how he gets his money to explore origin of life. Jim Tour is the nefarious one. That's Lee Cronin, but I'm the nefarious one. Here is what textbooks tell us are the characteristics of life. Responsiveness to the environment, growth and change, ability to reproduce, have a metabolism and breathe, maintain homeostasis, being made of cells, and passing traits on to offspring.
So what are the requirements for our living system? We need genetic code, we need mating, we need metabolism, we need adaptation, we need homeostasis. And we can build a system, and I can show you a flowchart.
I agree.
Which is, what is the most basic unit of matter that can undergo Darwinian evolution that you know of? And I suppose it won't be much of a surprise to see that it's a cell.
So you understand, these are the requirements for life. You said it yourself in 2012.
Lee has several papers that are relevant to this discussion, which we will refer to when appropriate. Let's hear him explain this one now regarding some interesting developments in autocatalysis, since we're on the subject.
Yeah, so in this paper, what we managed to do is solve a mystery that first started by Freeman Dyson. Freeman Dyson suggested that in chemistry you have these things called catalysts, and a catalyst is something that helps a reaction happen, right? It's a bit like a bridge builder builds a bridge such that cars can go from one side of a crevasse to the other. So it's kind of like a way of making sure that reactions occur. Now there's a special type of catalyst called autocatalyst. So it's a catalyst that makes itself. And so the more of itself, so it's a bit like, you can imagine a catalyst is like a bit like a template. You have some bricks that turn into a house, and then that house is able to make other houses, and that carries on going. And they exist in nature. But what I found in this paper, not only could I make one catalyst or one self-building house, I could also make a self-building skyscraper with them together. And what happens when they get paired up together, they don't just make houses and skyscrapers, but they make a whole bunch of them. So what does that mean? That means you can make molecules that can be like proteins and be like genetic material at the same time, mutually interacting. And they started off from an inorganic salt, as simple as table salt. And that was a mind-blowing result, because both Freeman Dyson and then a whole bunch of other people, physicists and biologists, predicted this, but until a few years ago, the simplest autocatalytic set, it's called, was quite complicated. It required proteins and RNA, which are already quite sophisticated materials with really complex blueprints. I showed in that paper how you didn't need a blueprint and you could still get self-making complex molecules.
Right, and we're talking about using a highly abundant mineral of some kind, so the prebiotic relevance is clear.
So yeah, in this case, you probably wouldn't invoke them as exactly on early Earth, but they are present. But what I would say, the general phenomena showing it could be possible with no information is really the key. What James is saying a lot is that there is too much information in the cell. So we're saying, hey, just with a bit of rust. In fact, it was a form of rust called molybdenum oxide. So the molybdenum metal is a little bit less abundant than iron, but I have no reason to believe or no experimental evidence that says that rust under the right conditions won't undergo the same process. So I think that that's an important thing about the need for some kind of advanced information to already be there, invoking this creator. That is incorrect. We've shown that is false.
Lee, your molybdenum oxide, your rust, is a bunch of nonsense. It is not life. It does not move toward life. You're getting autocatalysis, something that was shown by Oswald more than 100 years ago. And you're not making houses and skyscrapers. There's some more loose talk because people think that, wow, he's built skyscrapers like this. No, he's making micron-sized particles at best. Micron-sized particles. And he says that they're autocatalyzing. They're going from one to another. There's nothing there. He's just doing some autocatalysis on an inorganic complex. It has absolutely nothing to do with life. Absolutely nothing to do with life. And he's making this projection on this video about origin of life that this means something. It means absolutely nothing. There is nothing there. Did you have a genetic code? No. Did you have mating? No. Did you have metabolism? No. Did you have adaptation? No. Did you have homeostasis? No. Did you have life? No. And then you claim that in this video that I am invoking a creator.
So I think that that's an important thing about the need for some kind of advanced information to already be there, invoking this creator. That is incorrect.
Show me in my video series where I invoked a creator. But I'm the nefarious one. Let's see how I had explained autocatalysis and compare that to the explanation of Dave Farina's expert. So I described autocatalysis in my video briefly because I don't think it had a whole lot to do with this. And we'll show other so-called experts in origin of life totally debunk this whole autocatalysis being the end-all be-all. But in any case, before we get to that, here's how I had described autocatalysis that really upset Dave.
Another dramatic demonstration of Jim's cluelessness arrives when he attempts to discuss autocatalysis. You see, this is a phenomenon that synthetic chemists don't deal with because it is rarely encountered in traditional synthetic chemistry, which explains why he doesn't know anything about it. But bless his little heart, he sure tries his best.
Autocatalytic means that a reaction makes something, and that something that it's made becomes a catalyst for the next structure to be made.
Apart from this being a totally unsatisfactory and incomplete definition, he literally just moves on as though there's nothing else to say. Why? Because he knows it is a core concept for origin of life, thus it is in his best interest to ignore it, and he also has no ability to speak about it in an even remotely sophisticated way.
That's the way I described autocatalysis, which he says is a core concept. We're going to get to that when we start talking about the things that Dave has said. But let's see how Dave's expert Lee Cronin explains autocatalysis and compare that to my explanation.
Now there's a special type of catalyst called an autocatalyst. So it's a catalyst that makes itself. And so the more of itself, so it's a bit like, you can imagine a catalyst is like a bit like a template. If you had some bricks that turn into a house, and then that house is able to make other houses, and that carries on going. And they exist in nature. But what I found in this paper, not only could I make one catalyst or one self-building house, I could also make a self-building skyscraper with them together.
So there you heard his explanation of autocatalysis. So that was so much better. I mean, that's his expert. And James Tour's clueless because it's a synthetic chemistry concept. Well, Lee happens to be a synthetic chemist. Either you like synthetic chemistry or you don't. And then Dave somehow suggests that calcium hydroxide should not even be considered in the Formose reaction because for some reason he just loves picking on the Formose reaction, where I say the Formose reaction competes with the Cannizzaro reaction, which it does, and then I showed Dave some evidence for that. But let me just give you the context for this.
And finally, going back to individual nucleotides, there is the tidbit where I called James out for his weak argument regarding Cannizzaro reactions. He thinks that because sugars undergo these reactions in competition with the Formose reaction, prebiotic synthesis of sugars will be a total mess. Well, it's a really weak point because, again, Cannizzaro reactions would not lead to the type of molecules which are known to self-replicate and thus would not be selected for by molecular evolution. Yes, that pesky concept of selection that James pretends doesn't exist. But furthermore, because I correctly pointed out that such strongly basic conditions are not a given, he had to reference the original paper from 1861 that invokes catalysis by calcium hydroxide, as well as a Wikipedia entry which says that in mineral form it's rare but can be found in some rocks, in order to pretend that strong base is indeed a given and inescapable.
Then in Dave's same video, he starts talking about the Formose reaction, and he shows a reference. He should have read that reference.
An enormous amount of work has been done in this area since the 90s, so in examining real-world examples of autocatalysis, it would be much more impressive to fast-forward to present day. Below I will link this 2021 review of autocatalysis, which neatly summarizes the breadth of application this concept presents, only part of which is the origin of life. It covers essential background information regarding kinetics that James might want to study, as well as dozens of examples of autocatalysis in a variety of contexts, including the strictly organic and feasibly prebiotic, such as the Formose reaction he so frequently brings up.
Oh, there it is, the Formose reaction which I bring up. That's his slide. In his paper, which he cites, calcium hydroxide, which he feels is irrelevant because that wouldn't be available, but then he even shows a slide that says calcium hydroxide. Dave, didn't you even read your own paper that you're putting up there? You put it up there. It's right there, calcium hydroxide. Every time he brings up a paper, he gets it wrong.
I'm just excited to be in a place where I can read papers on those topics and kind of understand them, pretty much get what the paper's talking about. I know how to read papers. They're comprehensible to me, sometimes with some difficulty, but I understand chemistry. You can't it's not gibberish to me. I may have to look into stuff a little bit.
In his last video, he only cited one paper, but boy, did I have a heyday with that, because he cited it so improperly. Boy, I had a great time with this. That's exactly what he did in this series. In this series, you thought, wow, I'll be really intellectual. I will just go to the internet and grab a bunch of papers and put that in there. It's going to make me look really smart. No, it didn't, because every paper he had wrong. Every paper, when you look at the data, boy, it's just an embarrassment of riches for me to be able to talk about this thing. It's just so much that I can take from this to talk about it. But here's just one example with calcium hydroxide. And then he brings in his expert.
Let's check in with Lee again for how this type of chemistry can yield complex sugar-like molecules and RNA precursors.
So in this paper, we showed the Formose reaction, which is a really simple way of making sugars or a big mess. Normally, when you do the reaction, produces billions of products, literally within a few seconds or hours. When we added minerals, we were able to steer the formation. So not quite so many got made and other interesting things happened. And you could imagine a type of catalysis was occurring. It's still a bit too complex for us to interrogate, but we showed a number of important things. Number one, there was catalysis. Number two, we were making some interesting biological-like molecules that weren't present when the minerals weren't there. And number three, we were steering the chemistry, so it wasn't just getting more and more and more messy. We were able to make it less messy. And that, I think, is really important for the onset of evolution.
Wow, what a field day for me. I mean, this is just going to be great. So Dave shows this article, Taming the Combinatorial Explosion of the Formose Reaction, and this is by Lee Cronin. And so Lee starts talking about this. This is just from Dave's video. And Dave, you're going to have to read this. Right there is the Formose reaction, and what has he got? He used calcium hydroxide. Your own expert used calcium hydroxide in the Formose reaction. There it is expanded. Calcium hydroxide right there. So, you say in one hand it's irrelevant, and then in the other hand you bring it up from another reference, and then in your third hand, what you do is you go and you bring in an expert who uses this, and you didn't even notice it. You didn't even notice it. You just put it in there. And I'm telling you, the guy doesn't know chemistry. Dave Farina doesn't know chemistry. He doesn't know how to read a paper.
I know how to read papers. They're comprehensible to me, sometimes with some difficulty.
What did Lee say? Lee said within seconds to hours, you get billions.
Normally, when you do the reaction, produces billions of products, literally within a few seconds or hours.
Billions. Billion is a big number. Billions of compounds. Remember that Dave said you don't get such a mess because of this concept of autocatalysis. Oh yeah? He just said, your own expert said you make billions of compounds. Now he said he could make it so it made less of a mess. That's what he was claiming. So now let's start talking about Lee Cronin after we've exposed that Dave doesn't know what he's talking about because he can't even recognize calcium hydroxide in his own slides that he puts up there. Anyway, so here's the reaction. And what does it say? Indeed, in that calcium hydroxide. And then you just go to the experimental. Dave, you're going to have to read the experimentals. You can't just read the words that these guys write because they're not to be trusted. That's what makes you the victim. They're not to be trusted. Right there, calcium hydroxide in his experimental. But that's not the major point. We're assessing this, and the problem is that Lee Cronin really doesn't know anything about organic chemistry. He said it himself.
I'm an inorganic chemist, so I don't know any organic chemistry.
But let me take you through organic chemistry. You say if you run it under standard conditions, you get billions of products within a few seconds or hours. Precisely what I'm saying. You get a mess. Dave, do you see that? Your own guy said you get billions of compounds in the Formose reaction. Billions. So what does he do? He's using mass spec and mass spec of mass spec, and he's using not just high-performance liquid chromatography, but an ultra-high-performance liquid chromatography where he's trying to separate this out. He's getting all sorts of compounds. Now, each one of these dots is not a single compound. There's lots of isomers underneath them, and we know that from things that he's going to say later on in his supplemental to his paper. But you get lots of compounds. As you go through recursive cycles, does it seem like you're getting a whole lot less? No, you still get many. But why does he get less? Is it because he's really clearing this out? You got to look at the experimental. He says when he ran this reaction, then about 70%, 3.5 mils of the supernatant was removed for analysis. He's removing the supernatant. All the ones that are polymerized and are crashing out of solution are getting put away. They're solidifying and they're falling out of solution. They're precipitating. And then he takes the supernatant, he puts it on his HPLC, and he does the mass spec of mass spec analysis. But you're getting rid of 30%. And so, yeah, you're going to get less compounds. What if you had looked at the polymers that are there? You get billions and billions of polymers, trillions of different isomers. This is the problem with this chemistry, Dave. It doesn't work. This is what I'm trying to show you. Why don't you learn something from me? I'm trying to teach you this. He himself says it. You remove the supernatant because all of these things were polymerizing. It's right there in the experimental methods. Just read it. Lee Cronin somehow says you get less mess, less compounds, but he's removing the supernatant. Let me teach you this organic chemistry. I know you don't know anything about organic chemistry, so let me teach you about this. Could that mixture ever be used synthetically for anything? I ask you, Lee. Could that mixture, even after you've made it less messy because you let the ones that were really big and fall out of solution go away, could you ever use that for anything? No, you couldn't. Your UPLC mass spec of mass spec. Billions, does it really go to less or does it go to more? Maybe you had more, just that those precipitated out. You keep separating out the impurities. Welcome to my world of organic chemistry. It's tough. It's tough. Chemistry is a real mess. And now let's look at the next thing that he says in his paper. This is in the supplemental. So he's talking about how you can mix these compounds and you can start getting. Look at this. There's a ribose, but it's not really ribose because you don't have the stereochemistry. So he's not showing any stereochemistry here. And so look what he says. The exact isomer of the nucleoside was not assessed. Since the pure standards used for validation were not differentiated by their isomeric position. However, we believe this to be satisfactory evidence towards the presence of nucleosides in the product distribution ensemble, particularly within a mixture of this complexity. Yes, because you still have billions of compounds. Why could he not assess which nucleoside it formed? Why could he not assess that? Because there's so many different isomers. He couldn't even pick it out. You have all the different isomers. Look at all this utter mess. This is totally unusable, Lee. Totally unusable. This is a mess that could never be used. And it's so messy. I thought you were purifying this out some mysterious way. But still, you couldn't even assess what the isomers were because they were all overlapping. I'm telling you, each one of those dots on your little panel was multiple compounds. So if you think you're getting billions, you're probably getting trillions of compounds because you have all the other isomers under. Welcome to my world of organic chemistry. This is the nonsense that origin of life researchers put forward that they want us to believe they've really got this thing solved.
Let's check in with Lee Cronin again regarding peptide formation using wet-dry cycles.
So peptides, proteins are made of peptides, and the way you make peptides is you take things called amino acids and you put them together. In the chemistry laboratory, we cheat and use activating agents, and we heat them up quite hard, and we use these agents to make them. But what we showed is that if you could just put the amino acids together and dry them out and have cycles of adding water and then drying them, you could actually make these proteins with no activation. And actually, for me, that was kind of obvious, right? Everyone was saying, oh, it's hard to make proteins. It was a kind of hard, easy, obvious, although it wasn't, they said it was hard, it was obviously easy to kind of challenge that by changing the conditions. And that's what systems chemistry is teaching us, right? That it's not just about keeping, doing chemistry under one condition. By varying the conditions, by making them dissipative or having cycles, we could do interesting things. And so the really nice thing about this is that you've got these amino acids, you add water, you don't make any proteins, don't make any peptides, you dry them down, then you start to get formation. Then, when you make them wet again, they fall apart slightly but slowly, and then you dry them down and they reform again. You think about this kind of wet, dry. Actually what you get is a type of basic evolution, where it's almost a bit like if you've got a piece of clay and you're trying to mold it around a shape, and you let it dry out and harden, and it's not quite right, but then you make it damp and then push it a bit more, it gets better and better over the cycles. And of course, there are night-day cycles on Earth, and things get hot and things get cold, and there's rainfall. Yeah. So you can imagine how cycles are very important for driving complex chemistry, and that's exactly what this paper did.
In the abstract, he writes this. He says, studies have explored peptide synthesis on clays, minerals, at air-water interface, on metal oxide surfaces, and under hydrothermal conditions, resulting in very low yields, typically less than 1%. Of oligomeric products where N is greater than 3. The difficulty arises as the condensation of amino acid monomers to form peptide bonds in aqueous solution is hampered by unfavorable kinetics and thermodynamics. That is, the formation of peptide bonds is slow, and in aqueous solution the reagents are thermodynamically more stable than the peptide products. Lee, did you watch my video? You might have learned this from my video because Dave doesn't believe this.
Peptide synthesis in water is not a problem, James.
Dave thinks making peptides in water is no problem. The thermodynamics, kinetics, not a problem. You're going to get these things. And we'll get back to Lee's paper in just a moment. Just hang with me.
Now for the peptides. I talked about this briefly in my original video, and he didn't like it.
You're going to do condensation reactions in water? I don't understand why some would suggest that you do condensation reactions in an ocean like this, in water. How can that be? Tell me about that. How do you do condensation reactions in water? Have you any references on these claims?
Uh-oh, someone didn't do his homework. Peptide synthesis in water is not a problem, James, because it is not a matter of equilibrium.
So he says it's not a matter of equilibrium, but now we've got thermodynamics. Doesn't thermodynamics talk about equilibrium? Doesn't kinetics talk about barriers that go from one side to the other? And here he says you typically get less than 1% when you try to do these sorts of things. It's hampered. So your own expert, Lee Cronin, comes on, shows a paper, and it agrees with me, and Dave, you didn't even know it. You didn't even know it. He agrees with me. These things don't form. Unfavorable kinetics and thermodynamics. That's exactly what he says here. But now let's look at Lee's paper in more detail. So he shows this picture. This is from his article. He shows this picture, and let's see what we're doing. Now remember, in my video, I taught you about what peptides are. You form from the alpha amine of one amino acid. That goes to the carboxylic acid to form the amide of the next amino acid. And that alpha amine on that amino acid forms the new peptide bond, reacting with the carboxylic acid of the next amino acid. That is the structure of a polypeptide. So let's look at this a little bit more carefully. Here's the polypeptide, and you have your carbonyl. On the alpha carbon, you have a nitrogen group, and that nitrogen hooks on to the next carbonyl that was a carboxylic acid. And mind you, none of these couplings will ever go at room temperature without an activating agent. You have to have an activating agent. You can do it at high temperature, but it's very high temperature that are needed to do this, as we'll see. But in any case, you have to have the C terminus and going across to its N, and that N coupling to the next C terminus, and so forth. That's what a polypeptide is. You do not have side chain coupling. That occurs after formation. That's not something that you can deal with before formation. And so there's never coupling through the side chain. This is not something that you get through this peptide formation. The problem is that when these side chains are active, when they have active moieties that can couple, then it's a royal mess. You can't work with it that way. Let's look at making a dipeptide. Say we take two amino acids, two peptides, we hook it together, we get a dipeptide. That's called a dipeptide. So we go from monopeptide to dipeptide. Now there's only one combination if the two peptides are the same. Here they're both blue. But if we had a red and a blue, you can have red blue, blue red, red red, and blue blue. So just the dipeptides, it starts becoming much more complex as soon as you get two peptides in there. Now, instead of just a red and a blue, there are actually 20 different colors because there are 20 different amino acids. So think about all the combinations that you could have. And you can't stop this at just a dipeptide. That's not something that would stop because this can receive another one. So you can get some tripeptides, tetrapeptides, and it's just a big mess. But now let's consider the option when you have an unprotected side chain that is active. Remember, about half of the amino acids have side chains that are active. So we'll give the red having an active side chain, blue not having an active side chain. What are the combinations you can have? You can have red blue, blue red, red red, and blue blue. But there's more that you can have. You can now have red coupling via its unprotected side chain. As soon as you have coupling through the side chain, these are no longer dipeptides. That's now a big problem because it's game over now for the growth of this because once you have this coupling, this is generally going to be as irreversible as the main peptide chain, whatever your conditions are, or if you want to say as reversible as the main peptide chain. If the peptide chain can fall apart, these will fall apart. This ruins the construction. You have 10 of these, or about half of these having these reactive side chains. So once you have reactive side chains, then you have this problem going on. So let's talk about Lee's wet-dry cycles. He says it's like the day warms up and the day cools down at night. It cools down at night, warms up during the day. Well, what he does, you look at the experimental. Now, Dave, you got to look at the experimental to see this. His hot cycle is 130 degrees centigrade. That's 266 degrees Fahrenheit for 15 hours. To sterilize something, you heat it up to 121 degrees centigrade, 250 degrees Fahrenheit. He is at sterilization temperature. You're going to form life under these conditions? Wow, that is really a harsh place where you get warming up in the day to 130 degrees centigrade. That would kill any life that would ever want to form because it's sterilization temperature. But you didn't tell us that. Boy, that was hidden in the experimental. And poor Dave was the victim. He believed you. And then what is it that you got? What is it that you got? So now you dry this thing out at 130 degrees centigrade, which is blazing hot. and for an organic molecule like this, and then you'll cool this thing down. So what did you end up getting? Well, Lee, to his credit, didn't just use alanine and glycine, things that have no other functionality. He used other compounds, like here you have an extra OH here. Here you have an extra carboxylic acid on aspartic acid. Here you have an extra carboxylic acid on glutamic acid. Here you have an extra amine on lysine. So all of these are active side chains. So half of your amino acids have active side chains. Most people leave those out. They say, we're just going to do chemistry on this and show that it works. It doesn't work very well on these either. But when you have active side chains, these compete for the reaction sites. So you got to read very carefully in Lee's paper to find this. That's why I can understand why Dave never detected this. And he says, although fragments corresponding to linear peptide structures were observed, we also note that both branch structures and other forms of bonds, for example, esters, may have been formed. Indeed, given the presence of reactive side chains, this is not unlikely. Not unlikely is a weird way of saying likely. So it is likely that you got all sorts of structures that are not polypeptides at all. Once you have these side chains in here, these are branched. These have nothing to do with real life. You didn't make your polypeptides. You put in these other ones, even your crazy cycles of 130 degrees sterilization temperature didn't even make polypeptides. As soon as you have those functional, those half of the amino acids that have these functional side chains, you don't get it. That's why you have to do protection when you do synthesis in the laboratory. Exactly what I went over in my video. Lee, if you had really watched my video, you would have learned this. Remember, you're the one who said you don't know any organic chemistry.
So I don't know any organic chemistry.
So watch my 13, 14-part video. Watch it. You'll learn some organic chemistry. I go through and I teach that organic chemistry to you. You really need to watch this. And so I sent this to a friend of mine who is a peptide chemist. This guy has been studying and making peptides for years. And I say, tell me, do I have this wrong? I mean, how can he be saying he's making peptides? Are these kind of branch structures without having the alpha amine attacking the carboxylic acid of the one functionality of the next amino acid? Could this be right? Here's what he writes. Quote, it is interesting chemistry, but not practical for anything. In most circumstances, one wants peptides to be uniformly connected from amine to C-terminal carboxylic acid, with the side chains being free, unattached. The definition of polypeptide is a bit vague, but the vast majority of people would assume that only N to C-terminal amide bonds are being formed. There are, of course, exceptions in which side chain connectivity is desirable from a synthetic perspective, and nature will make these on occasion as well, but only through non-ribosomal synthesis. However, what neither nature wants nor chemists is an uncontrolled mixture, and the methods described, as the authors acknowledge, will certainly result in complex mixtures. Outside of speculative investigations of prebiotic conditions, I doubt anyone cares. Lee, nobody cares. Nobody cares about this except YouTubers who can't read the papers and see that you've made a bunch of junk. And your little origin of life community says, yeah, you made a bunch of you made garbage. You made garbage. You didn't make polypeptides. You didn't. You didn't have realistic conditions. You bought all the homochiral polypeptides, amino acids to start. You didn't use isomeric mixtures of these. No, you bought all homochiral and you put them together under unrealistic conditions, 15 hours at sterilization temperatures. And then you got a bunch of junk out that nobody cares about. That's origin of life research for you. That's one of the top guys in origin of life research. You wanted this type of analysis? You got it, Lee.
This one's moving around over here. That one's almost decomposing, almost falling apart, but they're wobbling. Can you see? They're like, there's no life in them, but they are wobbling around and getting excited and searching, vibrating. That one just split into three. Oh, and that one, that was pretty exciting, actually.
If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.